Okay, so I hope again that you had a nice and agreeable lunch. And I would like to continue with the chapter on the wind, on statistics of wind. It's where we have stopped last time. Actually, we discussed, let me recall where we have been. We discussed two things in the last hours. One was the distribution of winds over the year and how they are described. And you should remember that there is this called the Weibull distribution, which contains two parameters that you can fit. And one special case is this Rayleigh distribution, which has only one parameter to fit. So if you know the average, then you know the Rayleigh distribution corresponding to that average. And that's a very widely used approximation of the frequencies of winds over the year. And that can be used to compute the power output of a wind turbine. So that was one topic we discussed last time, and the other was about the boundary layer stability. And you remember that we discussed about stable and unstable stratifications of atmosphere, and that there is this concept of the dry adiabatic lapse rate, so how much air gets cooler when it rises. Yeah, if you take a volume of air, and now if your atmosphere cools down faster than this, then you have an unstable atmosphere, because it means that relatively speaking your air that moves up is getting hotter. And if you have an atmosphere that cools down slower than this, yeah, then you have a stable atmosphere. And most of the time the atmosphere cools down slower, so you have a stable stratification. And if you have an unstable one, it leads to lots of mixing, and after a while it gets stable again, of course. But there was a question in the break, so why does unstable occur at all? And of course, why does unstable atmosphere occur? It occurs because there's solar heating. It's heating the ground, then the air at the bottom is getting hotter, and that means that it tends to rise, and that's exactly what we know, which is producing wind and so on. Yeah? So it's actually exactly the morning when the ground starts to heat up, when the atmosphere starts to become unstable and motions begin to become turbulent. So what are the implications of turbulence on our wind turbine is something I wanted to discuss and tell you how people so to say, try to describe turbulence. And this is what I want to discuss now. So this chapter is already in the notes that I distributed, I think, a week ago, but it's called the spectral properties of wind. So it's the time that matters now. Until now, I didn't assume anything about the wind at 1 second being somehow correlated to the wind at the next second, but in fact it is. It is, of course, highly correlated. And so the spectral properties of wind are basically the correlation of wind, yeah? Autocorrelation. And power spectral density are our topics here. Just to give you an example, if you look at sound, yeah, when I talk to you, what you experience is actually wind, right? I mean, your ear is getting compressed and uncompressed a bit, because we don't call it wind because it's at such a high frequency. But about sound, we very often talk in terms of spectral properties. So we say this is a high sound, this is a lower sound, and so on. Yeah? In reality, it's just pressure variations. And the same thing we can do with wind. So we can just look at the speed of wind as a function of time. And you remember that's what we did before, right? So you can look at a time series of wind data. So that could be wind speed over time. And here is wind speed. And now the question is what frequencies are contained in that signal. And if you would regard a time window which is finite, then we would just take the Fourier series, right? So then we could just take our finite window, take the Fourier series, and then we have a spectrum of that same time series. If you have now something like wind is an infinitely long signal, so it is actually starting, so to say, I mean, before humanity existed, there was wind already, right? And then it goes on until hopefully 5 billion of years until the sun is dying or something like this. So there is a extremely long time series, and it is, so to say, the equivalent for infinitely long time series of the Fourier decomposition is actually the power spectral density. It's, so to say, the frequency content per time, right? Because if you would have a very long window, then your Fourier coefficients would all go to infinity, so you need to divide by the length of the window, basically. And so now if you look at time series data and you create the power spectral density, I will not discuss the details here, but just tell you what it roughly is. It's like a Fourier transform. But for a signal which is not decaying, I mean, it's continuing. I mean, wind will always be there and will remain there. So if you would just take a Fourier transform, it would lead to infinite entries everywhere. But if you normalize it, so to say, by averaging, then you get what is called the power spectral density, usually denoted by big S, as a function of frequency. So here we would have frequency, and I call it F. Yeah? And frequencies we can either measure in hertz, but we can also measure them in the time scale of their period length, which I find more intuitive. And so you could say if the frequency rises, the time scale is going down. So here I could say this corresponds to 1 second. Here somewhere maybe to 10 minutes. And then I might have some other things which are maybe like 2 hours. And then this could be maybe not 20, let's say 8,760 hours, which would be a year, right? So there could be a logarithmic scale of frequencies and corresponding to these time scales. And then I could plot the power spectral density, and typically people normalize it with F because it's anyway decaying, and so that you can see a bit. And this is something that's not easy to produce. I mean, you would need this time series which is extremely long and contains very high frequency data. But conceptually people did that once, and at some locations at least it looked like this, so that you had some peak that is I think roughly something here, then something a bit in this area, then it's going down, and then there is another peak here. That's, so to say, how spectral densities of wind look like, and the meaning of this is relatively intuitive. Let me just explain the meanings of these things. This is what we call the diurnal peak. It's day variation, so that's roughly here like 24 hours. I forgot that point. So it's something that is in the scale of morning and evening. So that's obvious that wind has a kind of frequency component that it's always stronger in the morning, and then the evening it might be lower, and then the next morning it's related to the wind. So let me remove this. Here I need something, this is more, that's called synoptic. Yeah, so that's a word that I never used before, but I found in this wind literature, so I will also use it. So the synoptic peak is, so this is daily variations. And the synoptic peak is due to weather variations, like you see today the weather is like this, and tomorrow it's likely to be similar like today, right? And then there is maybe sun for 5 days, and you see there's these yeah, it's in the range of weeks or something like months sometimes, weather system variations. So there is maybe 10 days without any wind, and then you would see this in such a peak. So there's frequency content in that time scale. So that's maybe less intuitive and might also exist at some locations stronger than at others. There are some places where you have monsoon winds and so on, and then it's like there's something in this time scale of a year even. But what is always there, and that's the thing that I want to discuss now, is some frequency content in the lower range, like below 10 minutes in the second range, right? And that's what we call the turbulent peak. And that's actually the thing that makes our wind turbine design difficult, because turbulence is what, I mean, your turbine thinks this is the speed, but then suddenly the speed is a bit lower, a bit higher, and this is really what causes your turbine to start to oscillate and so on. So it's in the same time scale of our motion of turbines, and so that's a nasty thing. And there is sometimes in between, and that's also very often observed, might be different at different locations, but very often there is, so to say, a spectral gap. So you don't have so much frequency content between 2 hours and 10 minutes. Yeah? So if there's variation, it's like on a time scale relatively slow, or then a bit longer, roughly speaking. So let me discuss what we call turbulence and how we define it. Yeah? Because of the spectral gap, one very often takes 10-minute averages. I think that's like you take basically second samples, for example, yeah, over 10 minutes. Yeah? So definition of turbulence for us, of course. Huh? Definition of turbulence intensity. So how do we define turbulence intensity? It's something that can be different every 10 minutes, but you take a 10-minute sample, yeah. Let me just explain how is this, yeah, like 10-minute time series. And this could be seconds or a bit less even, yeah? And sampled at seconds or finer. Seconds. Typical measurement devices have they can measure wind speed at second sampling rates. And so then you can compute the average, right? U bar is actually, if you think of it, it's the number of samples. That's clear, the average. Yeah, then we can also compute the standard deviation. Just for fun, I write down the standard deviation of this whole thing. Then it's the sum of the squares, right? Ui minus u bar squared divided by n minus 1. And then we would have this the variance of that sample. And then you just, the paint is here, you have 10 minutes and you sample at seconds. But then you just say turbulence intensity is the fraction of standard deviation by average. Sigma u divided by u bar. That's it. So how much variation do you have on average compared to the strength of your wind? If you have very small intensity of 1% or something, then you know that your wind is most of the time really close to the nominal wind, and if it's 50% or more, then you know it's fluctuating a lot in this 10-minute interval. And of course, there could be very turbulent times when you have, for example, an unstable atmosphere, and there could be much less turbulent times at other times. And this is like one quantity I wanted you to know about. So the main point is it's about averages of some certain type. U bar is 1 hour, or 10-minute average. Yeah? Maybe up to an hour or something. But it's not the yearly average like what we had before. So that's a bit misusing the same symbol for another thing. It's the average now over 10 minutes and not over 1 year. So that's one way to look at the spectral properties of wind. But there is also another one which is actually mathematically extremely related. via the Fourier transform, and that is something I find a bit more intuitive, and that is the autocorrelation. I mentioned it already at the beginning. So autocorrelation is something that tells you how is one point in your time series correlated with another point which always follows, like say 5 seconds later. And when you think of a wind turbine, and if you look at wind measurements, then typical behavior here is that, I mean, the wind like 1 second later is probably very similar like the one that I have now, and maybe in 10 seconds slightly different. And maybe at some points, and that's actually due to the fact that we have eddies traveling through the wind field, I mean, at some point your wind might even reverse. So, I mean, you get, so to say, gusts, the wind is a bit stronger than the average, and then 20 seconds later you get a bit lower average than average wind, because the, let me just tell you, so to say, a picture. So if you have here the ground, and then you have here your big wind speed, what you might have is that, so to say, some eddy flowing through your wind speed. Let's just think of a rotation, for example. Let's make it this way, for example. So you might have some rotation superimposed to your general flow, and then you see that when this eddy, I mean this rotation thing, is traveling in the same direction, and when it starts, well, this is maybe I rotate it the other way around to make it how I described it before. So I improvise this picture, but it's not very useful. So there will be just some more wind at some point, right? So when the eddy is there will be a bit more wind. I think I need to think a bit more to make a better picture. So let's not exaggerate with the pictures. It's turbulent. There will be eddies in all directions and turning, but somehow the intuition I wanted to give is that at some point your eddy might be in the same direction with your wind, and then it superimposes it, and some later point you will get maybe the other direction of the wind, and then it will be against the wind. Yeah, maybe I should also take 2 eddies together. That's maybe a bit better, then I would have the picture. Yeah? So if you have 2 together, and they are traveling both in this direction, then you would, now I turn it. Okay, so then you would have first strong wind here, right? And then later you get a reduction in wind, and that's related to the fact that these 2 eddies turn here. And so it might be that if you look at the averages of 20 or 30 seconds behind, that then you might get anti-correlation. So that if you have a positive deviation, you change with a negative one. So let me just think about autocorrelation. So what is autocorrelation as a definition? And I think, if I'm not mistaken, my definition is a bit wrong. So if you have time series sampled with delta t, it's a sampling time, and I want to have autocorrelation as a function of time, so I introduce an integer r, and r is what I call the lag number. Yeah? So it's just the number of samples I'm lagging, and r times delta t is what I would call the lag time. It has a unit of seconds, and it's much more intuitive, so I get rid of my sampling time again. And so if I want to define autocorrelation, and I regard actually my wind speed variations, yeah, then I would just say it's the ui minus the average. I would check my average out here, and I correlate it with the sample that is like r time steps into the future, right? And I can only do that, of course, for samples which are where both these exist, and then I take my numbering should start at I think I do it this way at 1, but then I need to stop at n minus r in order to be able to still produce this number, right? And still have a sample, and then I also divide by 1 over n minus r, of course, because I had to throw out some samples. And then I also normalize this whole thing by standard deviation, and then I just divide it by sigma u squared, this number here. And then I have a correlation, and it's an autocorrelation because it's between the same quantity. And so you can plot this function. I mean, the longer your sample, it doesn't change because you normalize it with a number of samples and also your variation. But then you could plot this function as a function of time. And at your point 1, I mean, if you have 0 lag, you basically get this number here, the variance, and you divide it by the variance, so you will have 1. So this, and then this curve typically goes down. And that would be the function r of t, the autocorrelation function. And what is interesting is that this somehow very often actually goes through 0. And so at some point you begin to get an anti-correlation. And this time here has a specific name, and that's what I wanted to give you as a name. That's called the integral timescale of your wind turbulence. It's of course a time, something in seconds, could be 20 seconds or something. And this integral timescale basically tells you where your velocity starts to be anti-correlated with each other. And you can also try to go back to this picture here. Yeah? So there's basically, it tells you how big are the structures that are moving here. And so when I say this integral timescale has something that I call big T, for example, yeah? Then I could ask myself, what size of these structures does it correspond to that are traveling through my wind field here? And of course, for that one, I would also need to relate it with the average speed. So the average speed is here, u bar. Yeah? And so I would like to have a kind of length scale here, L. And this length scale is of course related to the time by the average wind speed times the time scale. Then I would get the length scale, right? I mean, it's meter per second times seconds is length. And that is, roughly speaking, I mean, it's the size of the structures that are disturbing me. So there's like, while I'm sitting here with my one position, my wind turbine, I see that wind is sometimes stronger, sometimes lower. And it is perturbed by structures which have, so to say, a typical duration of time t. And then I can try to get the integral length scale out of that. L, and that's I get from the average speed times the integral time scale. That could be like 500 meters or something, and that means that there's some quantities, turbulences in the air that travel through the air, which have time scale, length scales of 500 meter. Yes?
Why are there these alternating ends?
I mean, this is as I said, I want to think a bit more about having a good picture for that, right? But anyway, turbulence means there's eddies. Yeah? So if you have turbulence, then you see that there's a rotation in your flow in a non-ordered way, right? It's not like always in the same direction and so on. And these things persist for a while. I mean, if you look into water flowing in a river, then there's sometimes these eddies and you see them moving, right? And the same thing happens in the air that flows through us, so to say. There are some things that are just rotating motions superimposed to the length motion. So eddies are related to turbulence. Yeah? If there would be nothing that, I mean, if it's all straight, there would be no turbulence. Yes?
Could you explain the concept of the lag time and lag number?
Okay, sorry, yes. So I have a sampling, I mean, maybe I should just explain this thing again, right? So what I have here at the top, I could also just say I have samples. And I will have samples of that. I will not have it. And this sample time is delta t. And this is where I have my numbers. Maybe I should just explain this is, so to say, u I, and then this time here is actually I times delta t, right? so the sample at some time. And my lag time is now, I mean, if I compute autocorrelations, I need to relate this with another one. Let's say here's I plus R. Yeah? So this could be, this is U, I plus R at that moment, right? And so now that means that I'm R steps away, but because I'm actually computing a correlation, I will average the product of this deviation and this deviation. I mean, they are both deviating from the average, right? So that's the average, the same average. So you can compute their product, the product of these deviations. And that's what I compute here. And now I average that over all possible pairs. So I also compute it for this one and this one, for example. Yeah? And then so on. And I do it for all possible combinations that I have in my time series. And because here it's a finite one, I actually stop at n minus r, so that I can always have the lower and the upper one. So I'm computing these averages, and they are called autocorrelation. And they correspond, I mean, I compute them, of course, only for discrete r's, or like 0 would be actually the autocorrelation with yourself, right? 1, the lag number 1 is actually the corresponding, how does one sample correlate with the next? And if I have 2, then I'm correlating my sample with the sample 2 steps later. But because a number of samples is not such an intuitive measure, I prefer to work with lag time, which is then the lag number multiplied with the time constant. And then I will actually have this distance here is actually delta t times r, right? And that's now something in seconds. And if it's 5 seconds, for example, it would just say, this here's, for example, 5 seconds, right? Yeah. And you have here a number, and that tells how is the wind at 1 second correlated with the wind 5 seconds later. And that's why lag time is a bit more intuitive than lag number, because lag number just depends on your sampling rate. I mean, physically, if you would sample double as much, you expect this diagram to remain the same, but only if you plot it with respect to lag time. Is that an answer to your question? Not really? Okay.
I watched a video.
Okay, no, but maybe other people have the same question again. Is the concept of lag time and lag number sufficiently clear for most or not?
But we
Yes?
need it only to get our integral length scale, yeah? Or
I mean,
we need
that's-
it somewhere else?
You could also just plot this autocorrelation function and just look at it, right? And that describes already a lot of things. Actually, this autocorrelation diagram contains, in principle, the same information as this power spectral density. I mean, this is something I should just say as a note. So they are basically the Fourier transform of the autocorrelation is equal or up to some factors, right? Equal up to some normalization factors, maybe to power spectral density. So the thing that I plotted at the beginning. So if I have, of course, only 10-minute samples, I will be able to reproduce some parts of my power spectral density, which is the turbulent peak here. And at different times of the year, it might look different, right? And at different locations, it might look different. But one way to describe, so to say, the autocorrelation function is that you look where it goes to 0, and then you call this the integral length scale. Yes?
What do you write? Equal up to?
Up to factors, to some normalization factors. Yeah. So I don't go into details. I think this normalization here I would need to take out, and then it's very closely related to the power spectral density. Yes?
To normalize, you divide by the standard deviation.
Yes, exactly.
So is sigma squared the standard deviation?
Yes. Sorry,
The
no.
intensity is a sigma.
No. Sigma squared is what I need to divide here because it has the units of u squared, right? Sorry. Standard deviation is, of course, this is variance. Huh? I mix these things, sorry. Variance and standard deviation are related by x squared. Yeah? Variance is standard deviation squared. Okay. And so maybe in the break I think more about a good explanation of how the eddies look like. But the main message is there are some structures which are, so to say, traveling with the wind. Yes? You have another question.
Could you name an interpretation for anticorrelation in long times?
Sorry?
Could you name an interpretation, physical interpretation?
Of anticorrelation? Okay, so I was asked to give an interpretation of anticorrelation at long times. I mean, it's not, at some point it might be going up again, right? So I should say this is not like a typical feature that's always there. So why does some turbulence come? It's actually, maybe I should just say, so if you have an average wind speed, then there's a gust, yeah? And after the gust, it actually, there is a relaxation period where your wind is actually lower than average. And then there comes the next gust. So that's a typical behavior of a wind speed. And the interpretation I tried to give here, but I need to think longer about the geometry of this to really make it happen. But physically, if you just would think of what it is, what I have here, I mean, a typical gust, it's actually a zoom into this picture. So it's T. So you might have your wind speed on average like this, right? And then there is something like stronger wind for a moment, and then it typically relaxes before it's getting normal. That's what typically happens. And this is somehow indirectly, I think you can interpret it by eddies. Yeah? So at some point there is, so to say, more wind, and then you are at the other side of your eddy, and then there is less wind. So that's why it's also interesting to define the length scale of the structure. That's really, yeah. I should have plotted that picture before, but it was never plotted somewhere else in textbook, so I didn't find a good interpretation yet in a nice picture. Okay, other questions? So if not, I already, I just want to say there's like the quantities to remember here are maybe mostly that like turbulence is something what happens in 10 minutes and lower, right? Below 10 minutes. Huh? If you have a variation from like one day to the next, you don't call it turbulence. You just call it daily variation or something. But if you have inside a 10-minute interval, you have a lot of variation, then you call it turbulence. And you measure it typically by the relative size of your standard deviation compared to the wind speed. That's like the one thing to keep away. That's what people use, like turbulence intensity. And then something that like very refined already is that you could say, how is this this turbulence autocorrelated? And then you might talk about the autocorrelation function or about at least one number again, the integral length or time scale. And they tell you how long are the variations. I mean, how long does a typical gust take? Yeah. Roughly speaking, the integral time scale is the duration here, something, this time scale. How long do you get a stronger wind before it gets lower again? Yeah?
So this is just for typical time of, our gust.
Yes.
And then for longer times, autocorrelation.
I mean, you can, in principle, you can define autocorrelation for any long time series. If you would sample a year with 1 second, and, yeah, possible. And we tried to get some data series of that, but Rachel didn't find one, or they did not download fast enough, or whatever, right? So otherwise we would have asked you a question to do the full spectral density of a year. Yeah? But typically you don't have these data available. But I mean, I didn't have them. But in principle, you can define autocorrelation over for such a long time series, and then you might get, I mean, might go up and down, and it might be really interesting to look at it. But I didn't do it yet myself. Just the first zero crossing is called the integral timescale. And it very often exists. It doesn't need to exist, but it very often does. Okay, so if we have no other questions on this topic, then I would suggest that we maybe do an early first break, 6 minutes, and we start 10 minutes past 12, and then we continue really with another chapter. Because I want now to jump back to our wind turbines and rotor disk and actuation disk theory that we did already start due to Rachel's wake talk 2 weeks ago. Okay, so I guess everything works now. Did you check the sound? Yeah? Good. Okay. So I would like to continue as promised with more details on the aerodynamics of wind turbines. So now we leave the chapter on wind, which was a bit mixed. So now we are back in chapter 3, aerodynamics. And in particular, we want to move on. You remember that we did actuation disk theory already. So we actually explained why you cannot harvest the full wind that's blowing through the disk. And today we will derive wake rotation. Because behind a wind turbine, I mean one of these turbines that rotate, like the ones that we regard, because the wind turbine rotates, the air will rotate in the other direction. Very logically, because of conservation of momentum, right? So I will talk about wake rotation and what is called rotor disk theory. And the interesting thing is that most of everything that we have here can still be derived without going into the detailed aerodynamics of a blade. It's just from conservation of momentum. So maybe let me first recall one thing. So we remember this power, the power coefficient of a wind turbine based on the actuation disk theory. So this picture you remember, should always have. And then we derived the power coefficient as a function of induction, and this was 4a times 1 minus a squared, right? So this is like the power coefficient as a function of a. And that is actually, so to say, the proportion of the power that we extract from the available power. And it will lead to slowing down of the air by, you remember, my 1 minus a here, and 1 minus 2a at the far end. A was called induction. And because it is actually in the axis of our wind turbine, we call it axial induction. So it slows down the wind. And now the interesting thing is that because our wind turbine rotates, there is also something that we call tangential induction, because it's in the same direction in which the blade rotates. I mean, for rotating, it's only for rotating rotor disks. If you have a rotor disk, there is also here's there is a tangential induction. And there's a different number. Actually, maybe I've already explained it here. If you have a turbine that rotates with a certain rotation speed, yeah. So what you have here from top, let's just look at our turbine. So here we have our turbine with 3 blades, for example. But as I will say in a minute, the number of blades don't make any difference. So there is some rotation that your turbine has, right? And this turbine will harvest power by this rotation. And now it will have a rotation speed, omega, yeah? So that's actually the number, it's 2 pi times t, where t is the period of one rotation. It's the rotational speed. And so we know that the tip of our turbine here, if the length of the whole turbine is r, so this is like the radius of your disk, then the tip speed, as you remember, what will be the tip speed? It will be actually r times omega. That's why the omega is useful to define with a 2 pi. That's the tip speed, and if you are here at other locations, here for example, we call this distance from the origin, I should always go to the center, I call it little r, right? And the speed of our blade at r, r smaller than big R, is of course r times omega. No problem about that, right? It's the speed of your blade element here. And the interesting thing is, because your blade is actually pushed in this direction from the wind, you harvest the energy here in the middle, but that means that your wind, because of momentum conservation, it must go somehow to the right side here, because otherwise it couldn't push the blade to that side. So in that sense, you will get a wind speed motion in the other direction. And very often one scales it, with this number. So the tangential induction interestingly depends on R. And defined to be, so it's and let me just say, it's actually the if this is the speed of the air at the rotor disk, how much it's, so to say, moving in the wrong direction, then this speed is given by r times omega and then times a prime. So I prime is this tangential induction factor. Maybe I should call it this the factor. And it's this equation, and I should still say what V is the tangential velocity of the air, induced velocity of air in the actuator disk or in the rotor disk. So we will experience actually the same thing as before. You remember here, the wind slows down by a total of minus 2a. Yeah? But at the rotor disk, you see a reduced wind of minus a. And here it is the same. In the rotor disk, you already see it. So actually, your blades, when you are in a real wind turbine, your blades don't see wind that comes from here. They see wind that comes already from a bit of a bad angle, so to say, because of the induction here. And then afterwards, the wind will change even more if you're a bit further behind the turbine, and the total speed change is a bit bigger. Yeah? Total tangential speed after the turbine, tangential speed far behind is actually maybe let's call it this. I could call V1, and this I call it V, and this I call V3, right? That's in the same language as before. That would be R times omega times 2 a prime. So it will be even stronger later. So if I look at it from the top, let me just look at it from the top, so that I make my picture clear. So I look now here. Here's my eye. So I look in this direction here, from the top. And then what will I see? I will see, let's say the main wind comes from this direction. And then I have my blade, it's rotating in that direction. So this is my blade. Yeah. It's moving in this direction with a speed that is r times omega. That's clear. I mean, at a certain location, if I'm here at this cross section. And then it turns out that the wind must be deflected in this direction. And here I get, so to say, in the rotor disk, I get already the component. I mean, this is like the side component. Here's V1. And then if I'm far away, I would get V2. Actually, this is a wrong thing. So maybe I plot the velocity. So there is no side velocity here. Then there starts to be side velocity, and then there is side velocity in the whole wake afterwards. So after the whole wake will rotate. So here I have V1, and this is then V3. So you see that in the disk of the rotor it will already see something, but it will be by something that I don't derive now, why it's here just 2 times stronger at the end. Let's just take it as an analogy. We don't derive it here. But the point is there is a change of velocity, and we define our tangential induction factor by this formula, where V is of course the velocity in the rotation disk, and because in reality it's actually a rotary motion, we could also translate that to a rotation velocity. But interesting is that it depends on R, so we need to make our analysis for different parts of our blade separately, and that's a bit different to the rotor disk, to the actuation disk. So what we will need to do is we look at a little annulus of this form, so to say, and we see how in this length of your distance to the origin, how much angular momentum do you need to impart on the air in order to harvest the power that you wanted to harvest. And that will lead us very quickly to a nice formula what this induction factor is. So I maybe already say here one thing. The change of momentum in the tangential plane is of course tangential momentum. So to say the mass of the air times V3 minus 0, right? Because I have no tangential velocity at the beginning, so I basically get all this new velocity, and somehow this velocity is what creates this velocity change in my air is what creates my torque on my wind turbine. So here we are. So now I want to compute what size does the V3 need to have, and then implicitly what would be the induction factor. So at the end I want to compute V3 as a function of R for given A and omega. And now I think I need to also give probably the big R. Yeah, otherwise I don't know what to refer to. And of course I also need to know U infinity. I think there's a lot of things I need to know, but basically I regard a rotor disk as I know that this rotor disk is rotating with a constant speed omega. I prescribe this speed, and I also prescribe the induction factor, the axial induction factor, which determines how much energy I can extract actually. I could put it to the optimum value, but also to another value. But then I want to understand how much does the air start to rotate in the other direction. And implicitly, if I have the V3, I know also what is A prime is then given by this lower formula, of course. A prime of r will be then given by, let me just put it all to the other side, it will be v3 of r divided by 2 times r times omega. So that could be, if you want to have it in the as an induction factor later. But I find it easier from momentum equation to derive what tangential speed do you need. Please note that this tangential speed is actually also a rotating speed because it's in this whole disk. So maybe before I continue, I want to be sure that we are all on board with the pictures, and maybe there are some symbols which I didn't sufficiently explain. So please think of if there's some part of this picture, not the geometry, not entirely clear.
You wrote the
Yes?
U infinity. Is that the axial wind?
No, sorry. The U infinity. Yes, it's the axial wind. It's this wind, the wind far upstream.
About axial direction.
Yeah, the one that is not rotating yet. I mean, maybe I should first give the full picture, right? So there is wind, so to say. If you take one particle of air, it's just flowing like this, right? And then there is your turbine here. No? So that's your turbine. And then from this moment on, your particle of air starts to rotate in the wake. And it will not stop rotating if there's no friction. So what will happen with your wake is, because the turbine gets a torque, it will rotate the air in the other direction. Unfortunately, or fortunately, whatever. It's just happening. So we need to know about it. Yes?
If the wind is very heavy, will that speed the induction faster?
Mm-hmm. Of course, if there's stronger wind, then there is also more rotation. I mean, it's all relative, and that's why one defines also this relative, the tangential induction factor, right? Because, I mean, a typical wind turbine, I should also say, if you have more wind, you will also rotate faster, actually proportional in most of the time, and so then the distribution of this tangential induction factor will be the same for different wind speeds. That's why one defines it. But let's maybe, I think these questions are all not advanced, but I mean, they show that you got the picture, but maybe there are some more questions. If not, then I would just continue and try to derive by momentum balance how strong this speed change in the tangential direction should be. Tangential meaning in the direction in which the blade moves. And for this, it's useful to think at this annulus alone. And so we don't care about how many blades you have and how they interact with the flow field. The only thing that we care about is that there's an annulus, and from this annulus we want to extract a certain amount of power. And the way we extract that power is by something that is turning with a speed of omega into this direction. So there is some solid body, like the blades, that is exerting a force on this whole ring of air. And in doing so, it will change the speed of that air. You see? So, so we regard an annulus. And this annulus I will draw here. And I will regard infinitesimal. So to make it infinitesimal. An annulus is something, if you marry, for example, in some countries you put a ring on your, I don't have mine, anyway. But I'm married, but okay, most people have a ring, right? And that is called an annulus. Sometimes ring or annulus, but an annulus is this thing. Yeah. If you look at at this part of the air, and you put here your radius, and I want to regard the thickness of my annulus, and I call it dr, like infinitely small, but for the moment I just compute with it as if it was not infinitesimal. Yeah? Of course, you know that if you integrate over all annuli that you have from here to the big R, this would be the radius of the wind turbine, then together it would be the whole volume, right? So what is your area of this? So there's a certain area, I call it dA, right? And this area is given by 2 pi times r times dr. Yeah? Because it's very thin, I can actually assume this is, so to say, flat. It's the length of this modulus times the thickness of this ring, and then times the thickness, and then I get this volume. And of course, if I integrate from 0 to big R over this expression 2 pi times r times dr, what will I get? Let's just do this for an exercise because it's fun. I will integrate that, and I will, sorry? Yeah, I will get this integral 0 r of r dr is of course r squared by 2, right? And so I can put this whole thing here, and then the 2 cancels with it, and I get pi times big R squared. And that's the volume of our disk, of course. Yeah, just to bring you into the picture, right? So my area here, and then I look at how much power do I extract in this area. Yeah, so of area dA. dA defined by that. So I have this area. And how much power do I extract? Depends, of course, on my induction factor, but that's why I placed this here. So the power that I extract in that part of the annulus, maybe let's say the infinitesimal power extracted here in this ring, or in this annulus. So what is it? It's actually, I call it dP, the power. And that power is this expression that we had before. It's 1/2 rho times u infinity cubed, right? And then times the area, dA. This is now this infinitesimal area, of course, times the power coefficient, CPA. So that would be my energy that I want to extract here, depending on my desired induction. And then I know how much I will, in this ring at least, change my axial wind speed. But how do I extract that power? I extract it actually by rotating some blade. And so what I do is actually I move now my blade. I have a little something which interacts with my flow, and it's moving with a rotational speed omega, and with a real speed r times omega. So the speed with which my blade moves is, as I said before, r times omega. And so if I want to extract a speed, if I extract power with a rotary motion, I need to exert a force. My blade needs to get some force from the wind, which must be in the same direction in which I rotate. And this force will actually be harvested in the motor in the middle. Yeah? And of course, I will, if I have one blade, I will harvest not only the energy from that annulus, but also from this one and this one and this one, so from all the annuli together. But let's do the analysis only for one annulus. So the question is how can I harvest this power? And let me just move this up. I hope that this will work. To harvest exactly this power. This power with a rotary motion. motion with angular velocity omega, we need a torque. Yeah, and what is the torque? Torque is force. I mean, you need a force in this direction, which is of course distributed over the whole annulus, but this force must be multiplied with the radius in order to give a torque, and then you multiply it with an omega, and then it gives you a power. You need a tangential force. And I call it dF because it's the tangential force of this whole of this annulus. Yeah? So there must be some force with which this whole annulus, so to say, turns your wind turbine. And so you know that the power must be given by this tangential force times the lever arm times the rotation speed. You could either interpret this as a moment, as a torque, and then it's the product of torque and rotation speed that gives you power. But you could also say this is actually a speed, and I multiply it with a force. So I prefer now the force, because force is something I can easier relate to momentum change later. So this is already nearly everything we need in order to derive what we want to derive, because now I have actually equated the power that I want to extract with the power that I can extract with this rotary motion. And the only thing that remains to be used now is that if I exert a force on this whole on this ring, it means that my air needs to start to rotate in the other direction. So what is force? Just remember what it was, so to say. It's you could also say it's a change, it's a mass flow times. It's a mass flow times a change in velocity, right? That's actually what a force is, yeah? In our context. And so in this case, we need to say, due to momentum change. And then I'm back at my original picture. I have the zero speed in this direction, and then I will at the end have a speed of my air v3. So my change of speed in this tangential direction is actually v3. I can translate this all to rotation motions, but I think I prefer to work with this with the absolute speed. So here I will have, because my blade gets moved into this direction with some force, there will be a wind speed in the opposite direction, which I call v3. Yeah, and of course I can relate it to the actual induction factor, the tangential induction factor by this formula later. But what I get is actually my force dF, for this little annulus, is the mass flow through that little annulus. But what is the mass flow through the little annulus? It's actually, remember, mass flow through some area was rho times a times the speed. The speed was a infinity times 1 minus a, right? Because we have a slightly slower speed here. And now I make it an infinitesimal area. So I have rho times dA times u infinity times 1 minus a. So that's my mass flow through that disk. And then I change this mass velocity, I mean in this case the rotational velocity, from 0 to v3. So it's basically the change is v3, delta v, the change of velocity. Maybe I put v3 minus 0. So here I have, so to say, another expression for the force, which makes my force related to the change of the tangential velocity. So now I get, because I have a force, I must actually start to make the air rotate, and this is the relation between the two. And so now everything I need is to collect the two formulas together. I mean the three formulas, this one and this one. I mean equate these two things and then replace the force by what I have here. So that's what I will do now. So I put, maybe I give them numbers. 1 is the total power that I want to extract. 2 is the power that I actually will extract with my blade when it's rotating. And 3 is the change in tangential velocity that is anyway related with this force, must be related with this force. So I put them all together. I move a bit up. 1, 2, and 3 together. They will be actually, maybe I do it here, then I don't need to move the blackboard up and down. So I put this one expression to the left side, so I will cancel a lot of terms later, but anyway. Rho times u infinity to the power of 3 times dA times CPA. Right, that's the power, and that power should be equal to the power that I have here. So let me put this easy terms to the front, r times omega, and then I copy the dF expression that I have here. And now I have here a rho and a dA, and I have a u infinity, and I think there's something, no, probably not, u infinity, so 1 minus a, and then I have here a v3. V is now, okay, I use v for velocity, but it's now the tangential velocity, right? So this is now an equation that we trust, right? Because it's related to basic physical principles. So now we see that a lot of quantities here are canceling each other. The dA even is canceling each other. That's nice, right? And then there are some things which are remaining. And let me just collect what is remaining. So I have a 1/2, then I have a u infinity squared here. I have a CPA, then here I have an r times an omega times no u infinity, but 1 minus a, and then a v3. And please remember the v3 will depend on radius later. And okay, and now I can just relate all these things and what I will, let me first write this as a formula. So what do I get? V3 is equal to,
Sorry,
yes?
cannot we write our CP as our equation, and then we also can get rid of 1 minus c?
Yes, I can do that if you like.
And then it will be CT.
Yes, yeah, so, okay, that's interesting, yeah, right. That's a very good idea. So let's do that, just for fun. 1 to u infinity square, and then we have here CT. Yes, that's true. Please remember what is CT of A. It was equal 4A times 1 minus A. Okay. And maybe I directly write it down, then I have here 4a times 1 minus a, that's also nice, right? And here I have r times omega times v3. So now I have it further simplified, and okay, and now I directly divide by this, and then I'm ready, right? r times omega. So that's interesting. Maybe what you see immediately is even if you would keep the induction factor in the axial direction, in the direction in which we regarded the theory until now, if that would be constant everywhere, not depending on r, then at least still the velocity that we induce will be proportional to 1 over r. So that means we get more velocity the more we are in the inner parts of our blade. And that's actually true. And an interesting fact here. And I mean, you can massage this formula further if you like. Maybe first let's make a box around this formula, because that's already the main thing that I wanted to derive. So we have the V3 as a function of r. And now we could divide it by r omega again, and then we get our induction factor. Yeah, and maybe I already allow me that I make this to a 2, right? So this is it, right? Good. So this is now the formula that we will end with. And there are different ways of how I can, so to say, try to normalize it. And let me first get this a prime as a function of r. It's the V3 divided by 2 r omega. Okay, that's interesting. It's actually u infinity squared times a 1 minus a, and then divided by r squared and omega squared. Right, and the 2 is cancelled, so that's already a nice expression here. A bit nicer. But I think it also obfuscates one fact, namely that the absolute speed is growing with 1 over r. Yeah, the absolute tangential speed. You can use different expressions here, but whatever you do, the main picture is this. So if you think of your disk here and you look at how does the rotation here. So if your turbine moves in this direction, I mean your blade moves in this direction, yeah, so that's your blade rotation, then your wind will start to get some rotary motion, and it will get stronger the more you go to the inner part of your tip. And the strength is 1 over r. Yeah? V3 is proportional to 1 over r. For a constant. Yeah, so I say this is constant because you could in theory also make an induction, the actual induction different at different slices of your device, but that's not optimal. So it's optimal to still extract with 1/3 of induction everywhere. So A is equal to 1/3 typically for an optimally operated turbine everywhere. And so then you get this variation of your speed. And what is now interesting is that I think, and this is something I discussed with Rachel and others, and I think there is not a definite answer, but textbooks are contradicting themselves. So since 1935, there was a guy called Hermann Glauert, a British naval engineer, or aeronautical engineer, who derived something where he said, because this rotary motion will be kinetic energy. It must be lost to the turbine, and that means this. Maybe one thing I should say: if you rotate faster, this induction will be lower, of course, right? And so rotating faster induces less rotation on your wake. And so he argued that you would need a very fast spinning device in order to not have so much rotational energy in the wake. But later, and this is what at least some textbooks claim, is that this energy is actually not lost. Because it's, so to say, you can argue that this is actually completely energy loss free. It's just a rotation that is, so to say, imposed on your motion. And so textbooks are contradicting themselves. But what no one objects and where everyone agrees is what I presented until here, namely that there is induced velocity in the rotation, in the tangential direction, and that it is of this size. Yeah? So that's what we all agree, and then there's like little arguments if slow spinning engines, so to say, lose energy or not, and I tend to believe the newer textbooks, let's say, which claim there is no loss of energy due to the wake rotation. But as I said, aerodynamics is a complex domain, and it's, I mean, based on this theory, it's anyway a very crude approximation of the real flow simulation. And so people are not 100%, I mean, some people are 100% certain of this and others of something else, no? As sometimes happening in science. Let's conclude it here. As I said, I presented what we all agree, and anyway, the losses will not be very big if they would be there. And a guy called Glauert introduced these losses, and recently they have been argued away 80 years later. Okay, thank you very much. I suggest we stop here and we see tomorrow. Actually, tomorrow is an exercise by Rachel. Please click your forms, so what you did. Click whatever you think you did, right? Yeah. If you did it and at the end the answer turns out to be wrong, but you really did it and you have a justification why you did it this way and so on, I will discuss with Rachel if she subtracts too many points from you then, right? So please do the answers and do them as good as you can, and then click those that you did in the forms so that she has an overview of what happened. Thank you and see you tomorrow. Bye-bye.